Hi everyone, welcome to Privacy Now. I'm Mike Fibus. Whether it's detecting cancer sooner or spotting and preventing thieves from siphoning our bank accounts, the more the data scientists know about us, it seems, the more they're able to do for us. Now, for many of us, that can seem as creepy and downright scary as it is exciting. But does it have to be this way? Do we really have to compromise our privacy just to get the benefit of AI? My guest today doesn't think so. He's leading a team at Intel that's looking for ways to give information that data scientists need without impacting our privacy. With that, let me introduce Casimir Wierzynski. Cas is Senior Director at the Office of the CTO at Intel's AI Product Group. Cas, thank you so much for joining us.
My pleasure. Thanks for having me.
Yeah, so when this perfect storm first began gathering steam of pervasive connectivity, computing power, and data science capability, I think all of us were wide-eyed with the possibility. I don't know that many of us were thinking just how exposed we could end up becoming.
Yeah, well, overarching theme is that I don't think we need to panic yet, but we do need to keep in mind that the power of these AI systems, they really do rely on large amounts of data to work, and those data have to come from somewhere. It's just inevitable. So we have to find, how do we kind of unlock all of this power of AI fed by data, but still protect, the data and kind of societal norms around data. Yeah.
So I assume there are a couple of ways that you're looking at right now.
There's a really exciting set of technologies coming out under the rubric of privacy preserving machine learning. So I think everybody's heard of machine learning at this point. Privacy preserving machine learning is a set of techniques where you're explicitly in the math problem itself, trying to figure out how you can learn from data while still protecting the confidentiality and privacy of the underlying data.
Okay, interesting. And so just how would you go about doing that then?
Yeah, so it depends on exactly what's the machine learning task, but I'll just give you some examples. So for example, it turns out that, it seems like magic. It seemed like magic when it was first described to me, but there are ways of doing math, doing machine learning on data that's encrypted while it stays encrypted the whole time. And that's a technique known as homomorphic encryption. That's one example. There are, again, this seems a bit magical, but there are ways that you can have different sets of people who may have their own private data, silos, for lack of a better word. They can engage in some cryptographic protocol among them and essentially jointly compute some function of all of their data that without having to reveal to the other parties what their data are. So they can learn something collectively from all of their data without having explicitly to share it with each other. And so that's an idea known as federated learning. And then there's another kind of cool sets of ideas around how can you make sure that when you do machine learning on some data set, let's say each entry in the data set relates to a specific person, how can you make sure that the output of whatever you're doing doesn't reveal anything about any one particular member of that data set? And so that's an idea known as differential privacy.
Is one exclusive of the other, or for they different reasons?
There are some really interesting blends of these technologies that take advantage of the best of both worlds. So the classic example of homomorphic encryption is, I've got a picture. I want someone to do some kind of AI inference on that picture, tell me what's in it, let's say. But this picture is sensitive, it's personal, or whatever. I don't really want to share it with this other person. So I encrypt it, I send it off to this cloud service, and then it comes back. It only operates on my encrypted data. The answer that comes back is encrypted. In fact, it's the encryption of the answer that I want. And then only I can unlock and reveal the answer. So that's kind of the classic homomorphic encryption setup. Now, what happens if you have more than one party involved? Like, let's say again, let's take the example of the picture, and I want to run it through some AI model that depends on data from two other people now. So how would I do that? So there's actually some very cutting edge and very clever ways of combining homomorphic encryption and federated learning to have, to be able to enable these multi-party transactions like that.
Yeah, the federated learning sounds to me more like a twist on like an information exchange where there's AI kind of at the center and various data silos that you bring in what's needed from the different silos to get data big enough to do your AI to make some decisions.
Yeah, it's interesting that you should use the word exchange because, so in my prior life, I worked in financial services. I used to trade financial instruments on exchanges. Exchanges are a very powerful model for, allocating all kinds of resources, data as a resource. What excites me about these technologies is that there is the possibility now of kind of creating ecosystems around data. You've got certain sets of people who need it, other sets who have it, and you can still provide kind of the right wrappers of privacy and confidentiality around all of these transactions to make it work properly.
Yeah, so a lot of folks in the research community, have to get their research validated by their peers, and part of that is the hazard of making the data available. And I assume that's where differential privacy would come in to allow them to do that and yet still keep the information private.
Yeah, differential privacy comes up in a lot of contexts. That would be one of them. It's actually coming up in the 2020 census. So the US Census is going to incorporate differential privacy techniques so that, when I read aggregate statistics about, they're supposed to be aggregate, but imagine that you're reading statistics about some very sparsely populated part of the country. You may be able to infer from the average of something that it's actually, hey, there's only 3 people in this county anyway, so now I've learned something quite personal about somebody. So it's showing up in that setting. It's showing up in the setting that you just mentioned of people, they do a study on a certain collection of individuals, and they want to make sure that the results of those studies don't leak personal information. What's new and cool about differential privacy is that it's kind of providing, quantitative bounds on how much privacy is leaking or not leaking. So instead of kind of saying, well, I'm going to cross out people's names and addresses and hope that I've done a good enough job of anonymizing things, it actually has a, kind of a much more mathematical meat behind it to put, numbers on how much privacy is involved.
Yeah, and that's always, I guess a data purist, it seems hard to wrap my brain around the fact that part of what you're giving me is wrong.
Yeah, so you're getting at a very kind of central idea in differential privacy, which is utility. So, you're trying to balance, privacy versus utility. And it's there's a lot of really interesting research going on in this field. This is one of the trade-offs that they look at very carefully. I think one thing that's kind of slightly surprising is that in some cases, adding noise or adding privacy to the process of a statistical analysis can in some cases actually improve it. So if you have, let's say you're trying to fit some curve through a bunch of data points, if you assume that all of those data points are, super duper precise, then you're going to fit some very complicated curve through all of these data points, which is probably overly precise. And then when you try to extend this model to new data points, it's going to make very bad predictions. If instead you assume that each one of these data points is actually a slightly noisy measurement of some underlying true phenomenon, then you'll probably be a little bit more, you'll be more careful to capture the meaningful trends in the data and not overly learn the kind of the insignificant details. Details that would be insignificant, statistically, but would be very significant because they actually, would reveal some information about an individual in the data set. So
Right.
that sounds quite significant.
Right. Yeah. Okay. So that makes sense. In a sense, it's enforced curve smoothing in a way.
That's right. Yeah. Yeah.
So, what are some examples of homomorphic uses out there in the wild?
So in the wild, there are companies that are evaluating this in the financial services industry for testing out models of financial fraud. But I've heard, as you can imagine, some of these applications are fairly sensitive, so you may not read or get the full download. But I've heard of cases where banks are testing out the idea that they could actually use each other's fraud models as kind of a cross-check for fraudulent transactions. So imagine you have 3 banks, each of them individually has their own model for whether they think a transaction is fraudulent. They decide jointly, like, hey, if we could somehow kind of cross-check with each other, then we'll all gain greater confidence that some transaction is good or bad. But of course, they can't, under any circumstances, share what the actual transaction is. So what they do is they encrypt it. They use homomorphic encryption to do all that in the encrypted domain. So that's one example. There are some other interesting use cases in the healthcare system in Switzerland. The Swiss healthcare system is working with the EPFL, the Polytechnic and Lausanne, different ways of sharing medical records and doing inferences on medical records on encrypted data. So I would say it's kind of at early commercial proof of concept stages now.
Yeah, you'd mentioned healthcare, and to me that seems to be one of the more urgent, along with finance, uh, areas that really are in dire need of more privacy protection. I mean, the regulations we have in place never imagined the AI capabilities that we have today, or just how much data about us is out there today.
Yeah, those are 2. And then another area where I've seen it show up is around the area of recommendation systems. So, there's all kinds of examples where someone selling products or services may tailor that depending on your purchase history or different ways in which you've shown your preferences. But you may want to keep all those histories and preferences private. So could you have a system where, just for example, I send my viewing history encrypted to some recommendation system that then recommends a new movie to me, without getting all of my detailed viewing habits. That's something people are exploring.
Yeah. Do you think these three basic broad capabilities are enough to take us into the future and protect our privacy for the next however many years?
Well, so there's 2 aspects to that. One is these, and this is, I work at Intel, right? So one of the reasons that Intel is kind of trying to enable some of these technologies is that they require more computing power. And this has happened before in the history of computing, where suddenly everybody wanted to watch videos on their computer. And people said, oh my God, that's going to take much more computing power if everyone wants to watch videos. Well, once you get over some economies of scale, then companies like Intel can come in and provide the hardware and the chips to make that happen. So the same thing could happen in this space, and I predict that it will, where you have these kind of initial use cases like health and finance that are critical enough that they help build this economy of scale to make it much more widely available to other, almost every type of machine learning interaction you can imagine. Your question also involves, to save our privacy and so on. And there's more, I guess I should be clear that I think there's more to privacy than just data protection. There's all of these aspects around, giving users control over their data, awareness of who's using their data for what purpose. So all of that kind of control aspect of privacy is not directly addressed by the technologies that I've talked to today, but they're also important.
So you'd mentioned the computing overhead. I mean, how much of a piece of the compute equation are we adding here?
So when these techniques first came out in 2009, it was the original Craig Gentry, IBM paper on fully homomorphic encryption. I think the computational requirements were something like, millions of times more compute to do what you wanted to do, but on encrypted data. I think that factor of 1,000,000 has been steadily chopping off zeros over the last few years, and especially over the last 2 or 3 years, where people are looking specifically at cases of, okay, maybe we don't need to, if we restricted ourselves to encrypted math that's relevant to machine learning, so let's just restrict it to machine learning math, then we can get it to maybe within a factor of, between 10 and 100, something like that. If you told someone setting up a data center, hey, by the way, all the workloads that you do now are going to take 10 times more compute than they did before, that's probably not what they want to hear. Right? I mean, we're trying to get 10% better, 20% better on processors, and but I think maybe an easier way to think about the threshold or the kind of the gap between those two types of computing is in terms of the absolute level of performance. So, if let's say you're having a radiology image examined and you want to get some diagnosis, if instead of it taking 20 milliseconds, now it takes 2 seconds, that might still be okay, right?
Yeah.
So sometimes these factors of 100, you have to kind of look at what's the absolute performance that you need for the use case, and I think it's the level of performance now is at the point where real use cases are now feasible.
Yeah, and if if the healthcare industry, for example, updates, or I should say, when the healthcare industry updates their HIPAA privacy protection, then it may be a moot point. We'll take the 2 milliseconds. Or 2 seconds, I guess, instead of 2 milliseconds, because we have to.
Yeah, and sometimes even imagine, training some very complicated machine learning model across, let's just stick with healthcare as an example. Like, many hospitals want to pool their data to come up with some cancer diagnosis tool or something. That may take months to run, using encrypted data. However, imagine how long it would take for all of the various hospitals to be able to come up with some agreement to do it. And also, on top of that, using these cryptographic methods, you're not only kind of getting the agreement, but you're also getting some form of protection itself. So,
yeah, so you're right. It's a little simplistic just to think of it in terms of compute overhead, because there's a lot of other variables.
I mean, the compute overhead is definitely something that, my team is attacking on a daily basis. So that we understand, we're all over it. But I guess I'm just saying that, I guess I'm saying two things. One is that we've crossed a threshold where a lot of important stuff is now feasible. And let's not get too hung up on the, how many X overhead. Let's think about kind of the, the actual performance requirements for the job.
Last year I interviewed Professor Michał Kaczynski at Stanford Business School, and he basically says we're in a post-privacy era, that it's too late to protect our privacy. So that's really how we should go forward, is understanding that and living within that. Is that, I'm taking it that maybe that's not something you subscribe to?
Yeah, I don't know. I'm not ready to give up. I think, and maybe another way to think about it is, if you look at the exponential growth of data, I forget exactly the statistics, but probably in some short amount of time, we will have generated more data than previously existed all the time before. So, okay, there may be, what's out there already in some ways we can't control, but we can certainly get much more mindful about the future, and the data are going to explode even more. I think, I mean, coming back to your mention of the word exchange, I think that definitely a part of this whole puzzle, this whole ecosystem, you have to take economic incentives into account. So if we can kind of create a healthy economy around data, as opposed to a, you know, furtively kind of sneaking bits of data and not telling anyone, and then, you know, kind of like a good fences make good neighbors approach. Like if we think of these technologies as ways of properly fencing off and, you know, establishing nice hygiene among data sets and consumers and producers of data, then you kind of create all the right incentives for actors to be, you know, more in line with what we would expect. Another thing that gives me a lot of hope and excitement about the future in this space is you go to machine learning conferences. What happens in these fields often is that some new topics start out kind of slightly outside the main conference, and there are kind of these things called workshops where people are really working on very, you know, bleeding edge topics. The workshops around the areas of privacy and machine learning are just exploding, and in the main conference you're seeing many, many more papers now in this area of privacy and machine learning. So it's like you know, once you kind of orient all of that brain power towards these problems, you know, definitely culturally and kind of intellectually, the field is very much, you know, ready to sink its teeth into this problem. So I think that's a really good development.
Yeah, it sounds like. So keep at it for sure. What can't you believe I didn't ask you?
Um, uh, Maybe about what my team is working on specifically, like
Do
some of the
tell.
projects that we do. I work with uh, researchers and product people all across Intel, but a lot of the people on my team have been working on this area of homomorphic encryption specifically. And how do you make it more accessible to data scientists? Because, you know, it may sound all well and good that, you know, I want to have some machine learning model that takes encrypted data and gives you the answer, but, you know, I'm just a simple AI data scientist. I don't know cryptography. I don't want to have to learn all this software engineering. So the approach that we're taking is, let's take the software frameworks that data scientists are accustomed to working with now, things like TensorFlow and PyTorch and so on.
Mm-hmm.
And let's take advantage that they have this kind of compiler tool built into them. So they're accustomed in the machine learning world, we're used to having models that sometimes run on a CPU or on a GPU or on a neural network accelerator. So conceptually, you can think of these models also running on some kind of encrypted machine. So my team built this software library called HE Transformer. So it's Homomorphic Encryption Transformer. It lets somebody, a data scientist, write a model in TensorFlow or PyTorch, you know, as they normally would on normal data. Now, when they suddenly want to make it run on encrypted data, they just change a single line of code and everything gets recompiled to run encrypted. So that's a kind of a nice abstraction for data scientists, so they don't have to think too hard about the crypto. And then in the meantime, we can make the homomorphic encryption run as fast as possible. We can worry about optimizing that. They can worry about optimizing the data science. Another thing that my team is working on is standards, because, you know, this is cryptography. So you need interoperability, and you also need you know, you need a lot of eyes on the problem. You want everyone who's going to be, you know, academia, industry, government. You want as many eyes on these technologies as possible to make sure that we all have confidence in them. And then you know, so we and other companies like Microsoft, IBM, you know, various academics have been getting together periodically, workshopping, you know, what standards in this area would look like. And the most recent meeting was actually at Intel over the summer. That's another area where we're contributing resources.
Okay, it's definitely sound exciting, like exciting work, and certainly worthwhile. Kaz, thank you so much for your time and your insights. I really appreciate it.
My pleasure. Thank you for taking such an interest in this topic. It's a really important one. Thanks for having me.
And thank you all for watching as well. Until next time, bye-bye.